Welcome back, Shirley area, to the note video for Unit 2, number 9. Today we're going to learn about the periodic table and why it looks the way it does. Alright, so in the last note video, you learned about Mendeleev, you learned about Moseley, and you learned about the measurements that we have about the atoms that make up the elements. So we can tell by looking, just a little review. Remember, we can tell by looking at the atomic number, which is the number like here, that we know how many protons an atom, I should say, of manganese has. So if I were to say how many protons does manganese have, you would find manganese on the periodic table, look at that number, and that tells you how many protons it has. If I were to ask something like, how many electrons does boron have? Boron's there. If I were to say, how many electrons does boron have? If boron had no charge, you would look and you would see that boron has 5 protons. So if it has 5 plus charges, then it must have 5 minus charges as well. So you can say that boron has 5 electrons. What if I said, how many electrons does a +1 ion of lithium have? Lithium's right there. So if it's a +1 ion of lithium, lithium has 3 protons. Well, if it has 3 protons and has a +1 charge, that means it must only have 2 electrons. So if I want to know how many electrons a +1 ion of lithium has, it would have 2 electrons. And the last one here, what if I wanted to know how many neutrons, let's pick one we can read, how many neutrons does a sulfur atom have? Well, if we know that the total number of protons and neutrons is 32, and 16 of them are protons, 32 minus 16 tells us how many neutrons there are, and there would be 16. You will find very often that there is, especially when you're up here in the top kind of regions, that there tends to be the same number of protons as neutrons, but that is not always the case. If you start looking down here, it would be more like 108 minus 47, so that's definitely not the same. So don't think that protons and neutrons are always going to be the same number, but they often are in the ones that we start doing our calculations for. So a little bit of a review. So now let's see exactly why is it that we have this weird, funky, cavern-shaped riverbed, Grand Canyon kind of thing going on here with the structure of the periodic table. Well, when we talk about the periodic table, we're going to talk about them as periods or rows. I will call them both of those things. I will probably most often call them periods. So a period on the periodic table is going this direction. So starting here at K, or potassium, and all the way across here to Kr, or krypton, those are going to be in the same period. If you go up and down in the periodic table, so any of these columns, we call these families. They're also called groups. So if we started here with hydrogen and all the way down to francium, this family would be the column of the periodic table. So we have periods or rows, and we have families or groups, which are columns. Now, all of the elements in any given family, so any given column, they all have something in common, just the way that Mendeleev laid it out. They all react in the same way. They all have the same reactivity. And reactivity means the ease and speed at which an element reacts. So like I said when we were learning about the periodic table, that all of the elements in the first family, except for hydrogen a little bit, but these ones definitely, hydrogen's kind of like, it just doesn't quite fit in. But these ones here definitely, they all explode if you put them in water. Now there's various degrees of explosions. Lithium will kind of fizz and bubble. Sodium actually catches on fire. Potassium will literally pop. And then you get down here and it gets significantly more explosive. There is an aura that shows a video of it that's pretty impressive. Definitely impressive. It's usually a favorite. So any given column. So if we know, for example, how bromine reacts with something, we can predict that chlorine will react the same way, and that fluorine will react the same way, and that iodine will react the same way. So if you know how one element in a column reacts, you can predict that other elements in that column will react in a very similar way, just maybe stronger or weaker, but the reaction will still occur. Now this group down here, if this was the Grand Canyon, this group down here would be like the bedrock. These are called the expanded table. And specifically, this period in the expanded table is called the lanthanide series, and this period in the expanded table is called the actinide series. You do not need to know those terms. But the reason that they are down here is that in order for them to fit into the periodic table, remember, if they're in a column, then they have to have the same similar kind of reactions. Then all of them, this entire, oh, by the way, just so you know, periods or rows also have something in common. And that was the amazing thing that occurred when Mendeleev made this table. Not only does everything in a column have a similar characteristic, but all of the elements in a row also have a similar characteristic. So he ended up creating, this may sound silly because of the movie, but in math terms, this would be called a matrix. So this is a matrix of elements where it works in both directions, and as you will see, it also works on diagonals as well. You'll see that in a little bit. But anyway, in order for like the table to work, every single one of these elements in this period here would all have to fit in that space. Because this one's in the right column, this one's in the right column, but all of these all react the same way that Y does, and the same way that SC does. So we kind of say, these go here. And the same thing with these ones. All of these, they go here. And that's why the periodic table looks the way that it does. Now, there is a reason that these kind of towers occur on both sides, these like little planes and high places here. And you're going to learn about those later. But keep an eye out for that, because we're going to learn about other things about an atom. And as we learn about something new about an atom, it can be found in a pattern in the periodic table. So when we learn about something new, take a look at the periodic table and see if you can kind of see how that falls into this Rosetta Stone of a puzzle here. All of the information you'd ever want to know is pretty much in that table about elements. So let's talk now a little bit about what are elements like. So remember, these are the things that make up everything, not just things on Earth, but literally everything. The entire universe is made of these elements. It's pretty amazing that we have been able to figure them out, and had most of them figured out back in the 1800s. That's ridiculous. So very generally, we will call some elements metals. Now, all metals will share the same kinds of properties, and just so you know, most of the elements on a periodic table are metals. Metals make up the vast majority of them. So metals tend to be shiny. Oh, that's going to jump. Hold on. Back. Metals tend to be shiny, and here's a couple vocab terms. They tend to be malleable. Malleable means that you can hammer it into shapes. So this makes metals very useful. We can actually build things out of them, and we can take them and make them the shape that we want them to be. That is a very useful characteristic. They are ductile, so not only can we hammer them flat, but we can also pull them into thin wires. And that is a very remarkable feature. Imagine what life would have been like. I mean, now you have all kinds of wireless things, but none of those wireless things would have ever existed if they didn't exist with wires first. To be able to manufacture long, thin strips of metal, I mean, when you think about it, it's kind of like what spiders do. It's sort of like magical the way that they are able to pull that off. And all, don't be confused, spider webs are not made of metal. I didn't mean to make that misconception. And the other thing that all metals have in common is that they're all good conductors, and that is both of electricity and heat. They all have slightly different ways of reacting with things. Well, it's because they're in multiple different families. Remember, all the different families will react in similar ways. So since metals are spread across most of the families of the periodic table, they're going to react in very different ways. Generally speaking, though, this isn't going to mean anything to you right now. It's not going to mean anything to you until we learn about bonding. But generally, they will react by losing electrons. Nonmetals will tend to react by gaining electrons. And this is important to know, the most reactive metals are on the left of the periodic table. Those of you that have done the single replacement reaction will kind of find that to be true with that reactivity series paper. Nonmetals have properties that vary wildly. They are all over the map. They react in similar ways because they're all in a couple different families, but their properties, their like physical features and things like that, are wildly varied. Many of them, almost all of them, if you come across a pure sample of it, it would kill you. Many nonmetals are just poisonous, but one of the nonmetals is carbon, and that is what the structure of all life on Earth is based on. It is what makes Earth so special as far as, if you take away like the water element of the fact that, Earth has water and none of the other planets do, there is so much carbon on this planet that life is built from it. So nonmetals in general are poor conductors of both heat and electricity. Solid nonmetals tend to be dull and brittle. They crumble. So while the metals can be shaped and drawn into wires, if you hammer, if you hit a non-metal that's a solid, it just kind of breaks and crumbles and turns into dust. It's not very useful for that type of a material. The majority of nonmetals, so these are the solid ones. The majority of nonmetals, though, 10 out of 16 of the nonmetals are gases. So obviously you're not hammering those into anything. But that's what makes up much of our atmosphere. And then one of the nonmetals is a liquid, and that is bromine. It's also extremely poisonous. So most nonmetals are reactive with things. Fluorine gets the crown as the most reactive element in the entire universe. That's a big crown. You gotta have a big head to wear that one. And group number 18 is the group that's all the way on the right-hand side of the periodic table. They never react with anything. They're too good to react. They just stay over there on the right side of the periodic table, and they let everybody else react with each other, and they just hang out. They watch. We call them the noble gases. So there are lots of patterns in the periodic table. You don't have to know what all these things mean, but I just want to let you know that as you learn more and more about chemistry and you start to really appreciate this thing as a tool, there are patterns that as you go diagonals in the periodic table, ones as you go up, ones as you go left, ones as you go down. So when you are starting to learn how things react, and physical, even the physical features of them, like size of the periodic table, there's patterns all over the place in here. So here's the periodic table again. Let's kind of review what we just talked about. So all of these are metals. And the more left you get in the periodic table, the more metallic things become. So once you get down here, you are the most metallic, kind of most reactive metal that there is. Francium is the most reactive metal. It is the most metal of all of the metals. When you come up here, you are on the non-metal side of the periodic table. These are the non-metals. And just like when you go this direction in the metal side, it becomes more reactive. When you go up and to the right of the periodic table, you get more and more non-metallish. So that means fluorine is the most non-metallish non-metal that there is, and fluorine is the most reactive element in the entire universe. There have been cases, by the way, this is the noble gas column. These are the ones that don't react with anything. They don't react. But there have been cases where fluorine has wanted to react so much that it has actually forced noble gases to have a chemical reaction. And that just doesn't happen. So that just tells you how reactive fluorine is. Now, if these are the metals, and these are the nonmetals, these ones here in the middle are the ones that can't quite decide if they are metals or nonmetals. They're hedging their bets. They're not sure who's gonna win this battle, so they're playing both sides. They behave both like a metal and a nonmetal, and we call them metalloids. So metalloids have both metal and nonmetal properties. So since nonmetals are not conductors and metals are conductors, we call metalloids semiconductors. And this has pretty much made life as you know it as middle school students right now possible. If it wasn't for semiconductors, you would still be living like Little House on the Prairie. Think about that. That's big. That's a big change. So semiconductors have the special ability of being able to control how much they conduct electricity. And this is what made computers possible. Because computers work by having several circuits of paths of electricity, and then you can turn each of them off and on to run different calculations. Because the way computers work has to do with a whole bunch of ons and offs. Some people call it binary code. But it's nothing more than a whole bunch of ons and offs. So we can have all of this like circuitry on a chip, and we can control which of those circuits are actually going to run electricity and which of them are not going to run electricity at any one given time, and by doing that can make computer programs work. That actually reads the instructions in the computer program and puts the graphic on the screen, does all of the math calculations, whatever it is that computer is doing. That is essentially how it works. And we can do those because of semiconductors. So we can hit them with little bits of light, we can slightly change the temperature, we can do all kinds of little things with electric fields, and if you have the right field, that wire will conduct electricity. If you turn that field off, that wire will stop conducting electricity. So this has allowed us to make computers. The most common metalloid that is used to make computers is the element silicon, or silicon, which is why Silicon Valley, where they do all of the computer chip technology research and production, is called Silicon Valley. Germanium is also used, and so is arsenic, and I'm sure you've heard of arsenic. Arsenic is, it is poisonous. Surprise, surprise. Many elements are. Arsenic is used in rat poison, and it's really not good for you. This is actually one of the reasons there are there's places on our planet that are remarkably polluted, like really crazy polluted. And there is one place I saw a news show on once. It was over somewhere in Asia. I'm not sure which country, but somewhere on the east coast of Asia. And it is where all of the technology garbage gets sent. for whatever reason, whatever financial reason, that all of the garbage for technology, like computer bits and pieces, gets sent here. And because so much arsenic is used in like computer chips, if you're around a couple of them, it's not bad. Like, it's a very, very small amount. But when suddenly the whole world's pile of garbage computer chips, whenever you get a new computer or anything with a microchip in it, got sent here, it is like unbelievable levels of arsenic in the soil. It's really not, I would not want anyone to ever visit there, let alone live there. It's crazy. The rest of the elements are called synthetic elements. So synthetic is hopefully a word that you recognize. It means like man-made. So the entire, think about this for a minute. All of the elements, number 93 and higher, are synthetic. So when you look at the periodic table goes up to 100 and some now. They keep adding a couple of them. Everything 93 and higher was created by humans. That means the entire rest of the universe, everything in the entire universe, as far as we know, is made from element number 92 and lower. Element number 92 is uranium. That is one that you should know. You should know that uranium is the most massive, most number of proton, naturally occurring element. It can be considered the king of elements for that reason. That's it. It's the one that nature has as the grand poobah of elements. But on Earth, where humans live, we have been able to use science to actually add elements to nature. That is profound. That is unbelievable. We can actually create substances that never existed before and don't exist anywhere else in the universe. Now, that being said, there are substances in other parts of the universe that we can't create here. So there are things other places that we don't have. They think that there's metallic hydrogen in the middle of Jupiter. Well, we can't have that here because we can't create the amount of pressure that exists at the middle of Jupiter to create metallic hydrogen. But that's what we hypothesize is there. But the synthetic elements, so if you look at the periodic table, 93 and higher are all man-made. These are all things that would never have been found on Earth because we ended up making them in a lab. The very first ones that were ever made are, I keep hitting that button. The very first ones that were ever made were plutonium, which you've probably heard of, and americium. So these are the first two man-made, brand new, never seen before in the universe materials. This is a picture of plutonium. Oh, I hit that button again, sorry. This is a picture of plutonium. And this is plutonium. I believe this picture is of a sample of plutonium in a nuclear reactor. So plutonium is pretty commonly used to create electricity for millions and millions and millions and millions of people. It's not because plutonium is special in any way that it must be plutonium to run a power plant. If you don't know if you don't know how a power plant works, it's a pretty important thing to know how it actually functions. Essentially, it's just boiling water. You do the reaction that happens in a power plant every single day in your house when you cook anything on the stove. We're boiling water in every power plant that there is. And then that water turns into steam. The steam then turns a fan, and that fan is hooked to a motory thing that creates electricity. So it turns the mechanical energy of the turning fan, and it generates out of it electricity. You're just turning it from one type of energy into another. The difference between power plants is not that we're boiling water different. Like, it's not that, water is different. The difference between power plants is how we heat the water. So coal power plants burn coal to boil the water. Nuclear power plants just throw one of these things. Just throw one of these things down there, and it happens to be so radioactive that it's pretty hot, and it boils the water just from the pure heat of its existence. So while coal, you have to keep feeding it coal and keep burning the coal. You don't do that with a nuclear power plant. Now, there's big drawbacks with nuclear power plants as well. Because of all this radiation, it's very dangerous, as we saw in Fukushima, if something goes wrong. And also, it creates a lot of waste whenever, because this eventually gets used up. This material eventually stops creating enough heat to boil the water, and it just makes enough heat to make the water scalding hot. But if it's not boiling, it's not making steam, so it's not running the power plant. So, oh well, it's useless now. But the problem is it'll stay that hot for, a few million years. Yeah, that's a really long time. And we haven't quite figured out what we're going to do with it yet. We actually don't have any real plan. We started to hollow out a mountain over in Nevada called Yucca Mountain. And the plan was to hollow out this mountain, and we were going to store all of our nuclear waste there. And they spent something ridiculous, like $300 billion hollowing out the mountain, and then decided not to use it. It's kind of insane. I have a feeling there's something in that mountain, but I've actually been there. I took a picture of the sign for Yucca Mountain. It's right outside of Vegas. The other of the first made synthetic elements you actually have in your house. So that's kind of cool if you think about it that way. You have Americium in your house because Americium is what's used in smoke detectors. So if you think about that for a second, as we just said, remember, synthetic elements are elements that don't exist. This is a material, this is a substance, this is an atom that doesn't exist anywhere else in the universe except for the hallway outside of your bedroom. Because Americium is used in the smoke detector. So if you pull off the smoke detector lid, odds are you'll see something that looks a little bit like this. And inside that disc, which you should not pull off because it is radioactive, is this. And this is a chunk of Americium, typically in a ring of lead, because lead is very good at blocking radioactivity. That's why Superman can't see through lead. So it makes the radioactive material that's coming out of this directed in one way. And it's that unidirectional path of radioactivity that actually makes the smoke detector work. When smoke gets in the way of that radioactivity path, because there's like a sensor on the other side that is constantly picking up the radiation, that when smoke gets in the way, it actually blocks the radiation a little bit. And because the particles that are in the smoke, like the solids that are in the smoke, and the sensor then picks up on the fact that there's less radiation getting through, and it sets off the alarm. So if you get a bunch of dusty stuff in the air, you'll set off the smoke alarm because it'll kind of block that little bit of radiation. It's also why, if you ever look at this, it says you're not supposed to just throw away smoke detectors because we don't want a whole bunch of radioactive tiny discs in landfills and stuff. You're supposed to actually send them back to like a department. You're supposed to get in touch with the government to come and get them. Because, we don't really know what we're doing with all the radioactive stuff, because, like I just said, but, we're piling it all somewhere. So how do we make new materials? This is something that's pretty cool. If you think about it, humans have been trying to do this for as long as there's been chemistry. Before there was ever chemistry, if you think about like stories of olden days with like kings and wizards and things like that, they were called alchemists. And what alchemists were trying to do was change one substance into another. Specifically, I mean, this seems like a very noble pursuit, and it's like these alchemists were just trying to do this for the love of knowledge, but that is the furthest thing from the truth. Alchemists were trying to do it to be completely rich and have more money than anyone else and not have to do much to make that happen. Because what alchemists wanted to do was take lead, which was very common, apparently. As all the stories go, that I guess lead was easy to come across. I've never just found a brick of lead sitting outside, but apparently lead was very common. And that they wanted to figure out how to turn lead, which at that time was useless. That they didn't have guns or anything like that, so there were no bullets made of lead. They didn't do a whole lot with lead, but it was shapeable. They used to make cups and stuff out of lead and plates, which, yeah, then they were eating the lead, so that kind of led to some demise, I'm sure. But anyway, the alchemists wanted to take lead and turn it into gold. And gold was very, very worthwhile. That was a worthwhile endeavor if you could do it. Unfortunately, no one ever did. It never happened, which is kind of what led, though, to all of the attempts of people trying to turn lead into gold, led to pretty much everything we know about chemistry. So that pursuit of gold from nothing has led to our entire knowledge of chemistry, which is pretty awesome. So how is it that we were eventually able to pull off, essentially, alchemy? We were able to create new substances from other substances. We just never really did it with gold. You could. It just would cost more money to do in gold than you would get out of it, because this kind of a thing is not cheap. We use something called a particle accelerator. So, particle accelerator essentially takes atoms of one substance and shoots them through this big, long tube that, this is an aerial picture. I mean, this thing is miles and miles and miles and miles long underground, and it accelerates the atoms to as close to the speed of light as we can get. And then there's another tube that has another particle that we are accelerating to as close to the speed of light as we can get in the other direction. Then, sort of like a Matchbox car road rally setup, they switch the little lever and it makes the two pipes combine and the particles slam into each other with as much force as can possibly exist. At least on Earth. And we see what happens. Oftentimes, depending on what the test is, they want them to explode. And they want them to smash into each other and see what comes off. So and this is how they have discovered the subatomic particles. So, like I said, we've known about protons, neutrons, and electrons. It was through this that they discovered that those things are made of even smaller things, like the quarks and the neutrinos and the leptons. They learned that by having cataclysmic, apocalyptic, universe-shattering collisions. I thought hockey was rough. Another thing that they can try to do is fuse atoms together. So if you have a fairly good size atom and you kind of hold it in place in one spot in this tube, sort of, and then you send a multitude of other smaller, teeny tiny atoms, like at it and around it and through it, the idea is that eventually the big atom will hit just right, and it'll like go bloop, and it'll go inside and form with it. That the nuclei will actually touch. Because we haven't gotten to bonding yet, but you're going to learn that when atoms don't actually touch each other. The nuclei don't ever come in contact with other atoms. So when two atoms are touching each other, the nuclei are still worlds and worlds apart on atomic size. It's the electrons that have interactions with each other. But if you could line this up and you could shoot it so fast that when it collided just right, like a Robin Hood hitting the arrow just right, so it splits it right down the middle, that you would actually touch the nuclei of the big atom and the small atom, and they would become one. And that's called fusion. That is actually what happens in the sun. That's how a star burns. Stars burn by fusion. There's so much pressure in the middle of that giant object out there in space that it actually squeezes hydrogen atoms so close together that the nuclei touch and create helium. And that gives off a tremendous amount of energy, so much energy that it's the sun. We've never been able to quite do that on a sustainable energy source here. But on a tiny scale, that is what we do when we make synthetic elements. Actually, I dated a girl in college who went to work at this one over in Europe. It's pretty impressive. The very first element ever made using a particle accelerator was named Curium. And it was named after one of the most important scientists known to man, who you will learn about in a little bit. And they made Curium by slamming atoms of plutonium, which, remember, plutonium was already a synthetic element. They made plutonium a different way. By slamming plutonium with helium. And that ended up making Curium. So if you look at the atomic number of plutonium, you look at the atomic number of helium, and you add them together, you will get the atomic number of Curium, because they literally joined the nuclei together. So all of the protons that were in there are now in one slightly bigger nucleus. And if you ever look at a periodic table and you see some of them have 3 letters instead of 2, just so you know, the periodic table symbols. Some of them don't always match, like iron is Fe. The reason iron is Fe is because the Fe comes from the Latin for iron, which is ferrous. So if they don't have the same letter that you would think that they would have, it's because of some root or some other language, typically Latin kind of thing. But most of them are a single letter, like C for carbon or O for oxygen. But then if you add a second letter, that second letter is always lowercase. So when you're looking at a chemical formula for a compound, you can always figure out how many different elements there are in the compound by looking at how many different capital letters there are. Some of you saw that on the reaction action lab, where it was like FeO. Well, the Fe was the iron part, the capital O then was the oxygen part when you were looking at rust, or whenever there was the couple of sulfites on the double reaction. So anyway, that is how the structure of the periodic table is laid out. So know where the metals are, where the nonmetals are. A couple of the patterns there. The fact that all of the families have similar reactions. We still haven't gotten to what all of the elements in a period have in common yet. We're going to talk about that part of an atom when we talk about bonding. And at that point, you will know pretty much everything you need to know about the periodic table. So get ready for booby trap number 9, 10 questions. It's on all that stuff that we just learned about. And bonding is going to be coming up soon.